connecting your world.
Everything is running smoothly until, without warning, the entire network drops. No emails, no database access, no internal routing. The servers haven't failed, but the hardware handling their traffic has completely locked up. In this tutorial, we are going to build the exact setup that causes this kind of catastrophic crash. We'll trigger a switching loop on purpose, watch it overwhelm our hardware, and then step through the exact commands required to kill the loop and restore connectivity. Step 1 is establishing our baseline topology. We are working with 2 standard endpoint laptops, and each laptop is wired into its own individual network switch. To protect against failure, engineers build in redundancy. 2 distinct cables connect the switches in the center. This backup keeps traffic flowing, but that second cable wires a closed circle, the exact condition for a switching loop to tear this network down. The process begins with a simple, everyday request. Laptop 1 needs to communicate with Laptop 2. Because it doesn't know the destination's MAC address yet, Laptop 1 sends out a broadcast frame to ask for it. When that broadcast frame hits our first Layer 2 switch, it has to follow a strict hard-coding rule. A switch must forward a broadcast frame out of every single active port, except for the specific port where the frame originally entered. Since our switch is obeying that rule, it takes the broadcast from Laptop 1 and duplicates it. One copy travels across the top redundant link, while the second copy is fired across the bottom link towards switch 2. The first packet successfully crosses the top link, enters switch 2, and is routed downward until it reaches its intended destination at Laptop 2. But the second packet, traveling across the bottom link, arrives at switch 2 at the exact same time. Switch 2 does not recognize that this bottom packet is a duplicate. It treats it as a brand new broadcast frame entering its port, which means switch 2 is now obligated to apply that exact same broadcast rule all over again. Obeying its programming, switch 2 forwards this new broadcast out of all its other ports. That means sending the frame right back across the top cable towards switch 1. Now switch 1 receives the bounced packet. It registers a new incoming broadcast, applies the rule again, and fires it right back. The traffic begins to ping-pong continuously between the 2 devices, multiplying with every bounce. This loop happens because of a missing feature in the architecture itself. Looking at the schematic of a standard Layer 2 frame header, you'll notice there is no field for a time to live, or TTL, value. At Layer 3, IP packets have a TTL counter that ticks down with every hop, ensuring lost data eventually expires. Because Layer 2 frames lack this built-in expiration timer, our switches have no mechanism to drop these bouncing frames naturally. Without an expiration, the frames duplicate exponentially. Tens of packets become hundreds, then thousands, saturating the physical links with an endless feedback loop known as a broadcast storm. The switches are forced to process every single one of these duplicate frames. Within seconds, this infinite mathematical loop maxes out their CPU and memory capabilities until they freeze completely, dropping all legitimate traffic. With the hardware unresponsive, an IT engineer's immediate priority is stopping the storm. To do that, the physical loop has to be broken. Since the redundant cables form the circle, we can sever the cycle by forcing one of those links offline. Here on this terminal UI, we log directly into the switch and enter configuration mode. We target the specific port handling the second link. In this case, interface fast Ethernet 1/0/2 and execute the shutdown command. The moment that command registers, the port powers down. The bottom link physically disconnects, and the closed loop is broken. The storm of duplicate packets instantly vanishes because there is no longer a second path for them to bounce back on. CPU usage drops back to normal levels. With the loop gone, the switches recover, and a single stream of normal traffic safely traverses the one remaining active link from Laptop 1 to Laptop 2. We stopped the crash, but look at the cost. We had to intentionally disable our backup cable. Our network is functioning, but it is completely vulnerable to a single point of failure again. This leaves network engineers with a frustrating math problem. One link leaves you exposed to physical damage, but 2 links create a devastating broadcast storm. The solution to this problem is an automated protocol designed specifically to manage redundancy safely, Spanning Tree Protocol. Spanning Tree Protocol acts as an invisible network engineer. It evaluates the physical paths and logically blocks redundant ports to prevent loops before they start. If the primary cable ever breaks, the protocol automatically detects the failure and reopens the backup port to keep traffic moving. By tracking exactly how broadcasts replicate and overwhelm switch hardware, you have mapped the physical vulnerabilities of a network. That logic is the foundation required to configure a self-healing architecture. Now that you understand the physics of a loop, it's time to build the solution. Click on the next video where we will step through the process of configuring spanning tree protocol on these exact switches.